All right, today's notes, and yay notes by the way, today's notes are on acceleration. What I want you to do to start with, spend about 30 seconds, talk to your table, give me your best definition of acceleration. And you marks, get set, go. So, from what you've told me, you believe that acceleration is the rate of change in speed or the rate of change in velocity. And we remember that the rate of anything is how much time it takes. So what you're saying is how much time it takes to change your speed or how much time it takes to change your velocity. All right. Now, what I actually said the definition is the rate of change in velocity of an object. Now, this could be any change in velocity. You remember back a few days ago we were talking about speed and velocity, and I gave you an example where someone is driving down Twin Falls at 80 miles an hour. Now, they're cruising down Twin Falls. Once again, I don't recommend doing this. That would just be silly. But if you are in a car, you're cruising down Twin Falls at 80 miles an hour, and all of a sudden you see that nice police officer at the end of Twin Falls. What are you going to do? You're probably going to slam on your brakes. Is that a change in velocity?
No.
Okay. Quiet. So, if you're going at 80 miles an hour and you slam on the brakes, does that change your velocity?
Yes.
I've heard a lot of you say yes. I've heard some of you say no, because what I heard was that can't be acceleration if you slam on your brakes. But that's actually acceleration. Acceleration is any time you change your direction, any time you speed up, or any time you slow down. Acceleration is actually positive when you're speeding up, and negative acceleration if you're slowing down. A lot of you have heard the term deceleration. That's just a common or a layman's term for negative acceleration. So in this class we're going to be using positive acceleration and negative acceleration. Positive meaning you are speeding up, negative meaning you are slowing down. Now, what happens if there was not that nice police officer at the end of Twin Falls and you just kept cruising at 80 miles an hour? Are you accelerating?
No.
Why aren't you accelerating? Okay. So if you continue moving at the exact same speed, you're not changing it at all, you are not accelerating, but you can still move without accelerating, right?
Yeah.
You can keep going the exact same speed without accelerating. So, next thing that we really need to know is we need to know how to find acceleration, because we're going to be doing some calculations. We're going to be determining how much the velocity changes in a certain amount of time. So the things you need to know the velocities, the starting and the ending velocities, and you need to know the starting and ending times. So right here is our formula: final velocity minus initial velocity, final time minus initial time. So that little f and that little I, the little f means final, the little I means initial. The times, final time and initial time. And these are important because we don't want to get them backwards. This is what's going to tell us if it's a positive acceleration or a negative acceleration. So we'll know if we're slowing down if we come up with a negative answer. We'll know we're speeding up if we come up with a positive answer. All right, spend a few seconds, finish copying this formula and make sure you have it. Also make sure you know what the little I and the little f are. We do not want to get them confused. Very important to have them in the correct order. All right, we have an example problem. I do want you to work on this by yourself. See if you can come up with the correct answer. We have that pretty red sports car right there. It's going to start moving at 30 centimeters per second, In 0.5 seconds, it gets up to 130 centimeters per second. Calculate acceleration. When you are doing this, remember the 3 steps that you must have. I will give you credit for writing the correct formula. You must write that and write it first. I will give you credit for substituting in the numbers correctly. You must write that second. And I will give you credit for a correct answer in a box with correct units. On your mark, get set, solve it. All right, a little trick that's helped me, and something I like to do a lot of times when I'm solving problems like this. I have 2 different speeds up there, and I need to be able to differentiate between the 2. So I'm reading this, and it says starts with a speed of 30 centimeters per second. So I want to make sure I get this in the right spot. So I go ahead and I label this VF right there. So I put that little label over the 30, and then keeps rolling, and 0.5 seconds later, now I have to think, is this the final time or the initial time? Well, 0.5 seconds later, that tells me it's not the beginning, so that's going to be time final. And then I have velocity. Sorry, did I say? Oh my goodness gracious. Earlier I said the wrong thing. This is initial velocity up here, and this is final right there. Because we started at 30, we finished at 130. So the only thing I don't have labeled up here is initial time. Does anyone know what time we started taking these readings at? 0. So time initial equals 0. So it's one of those things, I just like to write it up there to make sure I'm getting all my variables correct. And now, we're going to go ahead. First step, obviously, is going to be writing the equation. Second step, we have to substitute in all of the different numbers. So our final speed was 130 centimeters per second. Our initial speed was 30. Our final time was 0.5 seconds, and our initial time was 0. I'm just going to do the math real quick to make it easier. So I have 100 centimeters per second divided by 0.5 seconds. Now, before you calculate this final thing, think about it. A lot of people make mistakes when they are dividing by decimals. So make sure you think about this and do this correctly. Last but not least, I do want you to put your final answer in a box with correct units. And the units for acceleration are centimeters per second, or that's the same thing as saying centimeters per second squared. So centimeters per second, or centimeters per second squared. The reason that is because we have centimeters per second right here, and we're dividing by seconds. So it's the same thing as just saying centimeters per second, and then once again we're dividing by seconds, so centimeters per second per second. All right, next example. We have our tortoise right there. He's running down the street at 2.5 meters per second. He sees the rabbit over there taking a little nap. And he decides to speed up some. After 3 seconds, he's now going 4 meters per second. He's still going in a straight line. So what is the acceleration? Solve it. You need a formula. You need to sub in the numbers, and you need to give me an answer. Go. All right, I went ahead and I labeled my variable to start with. The initial velocity is 2.5 meters per second. The final velocity is 4 meters per second. Final time was 3 seconds. The initial time is 0. Now I have my formula right here. Formula is acceleration equal to Vf minus Vi over Tf minus Ti. Plug in the numbers. 4 minus 2.5 divided by 3 minus 0. So 4 minus 2.5, I just did that math in my head, and I get 1.5 divided by 0.5. divided by 3. And now I get my answer as 0.5 meters per second squared. And you put that correct answer in a box. All right, so moving on. Now we're going to have to think back. Last week, we were learning about Amy and her bike trip. Y'all remember Amy and her bike trip? So there she goes. She's biking, she's just cruising, she's moving along. We had a graph of Amy. Her graph was a distance versus time graph. Well, this week, our graph is a speed versus time graph. It's telling us totally different things. We're going to talk about that a little bit more in a second. But to start with, some things I want you to notice or want you to point out. Where is the independent variable always located on a graph? Okay, it's going to be on the x-axis. In this example, our independent variable is time. Time's always going to be the independent variable. It's always going to be on the x-axis. Anytime you are creating a graph of your own, time will be the independent variable. What about the dependent variable? The y-axis variable in this case will be speed. And notice both of these also have the unit there in parentheses. A very good thing to put on graphs. So we have the dependent, we have the independent variable. What is the slope? Remember, slope is always going to be the y divided by the x. So slope of any line on any graph is going to be y divided by x. So in this case, it's speed divided by time. Didn't we just get a formula that told us what speed divided by time is? Speed divided by time. I think we did just get a formula that told us speed divided by time. We called it acceleration. So when we have a speed, like meters per second, we divided it by seconds, so meters per second. That does tell us acceleration. So this entire line that we have up here, this entire graph, is showing us the acceleration. So, when was Amy speeding up or increasing speed? We could also say, when was Amy accelerating? Is there any point on this graph that she's accelerating? Spend about 10 seconds. Talk to your table. Go.
Yes.
I heard a lot of answers there. And the question is, when she speeding up? She's only speeding up at one spot in this graph. That's from
0 to 3.
0 to 3. But could you say something different? If I asked, when was she accelerating? Would there be more than one spot? Yes, there would probably be a spot from 5 to 6 if the question is, when is she accelerating? Because remember, you can have both positive or negative acceleration. Next, when is her speed constant? And constant speed means no acceleration. 10 seconds, go. Okay, so constant speed means the speed is not changing. When the speed is not changing, you're going to have the same speed for a while. On this graph, we have the same speed from 3 seconds to 5 seconds. So anytime you have a horizontal line on a speed versus time graph, that means no acceleration. So constant speed means no acceleration. That's always going to be a horizontal line, and that's from 3 to 5 seconds. She's slowing down. There is a point on this graph where she's slowing down. We talked about that just a second ago. It has a negative slope. So the line is actually coming back down, and that means from 5 to 6 seconds, she is slowing down. Negative slope, negative acceleration, right there. Now I'm going to look at these two graphs next to each other. The one on the left is the one from today, the speed versus time. The one on the right is the one from last week, the distance versus time. We have lots of things that are similar and different on these two graphs. So right here, when I had a straight line going up at a positive angle, Straight line, positive angle on a speed versus time graph. What does that tell me? It is accelerating. It is constant acceleration. So Amy is speeding up at the same rate. On the distance versus time graph, right here, I have a straight line for that segment right there. On a distance time graph, what does that tell you about Amy? You're increasing distance at the same rate, so what does it tell you? That's a constant speed. So on the left side, we have constant acceleration. On the right side, we have constant speed. So even though those kind of look similar, they are very different things. You're going to have to be very careful when you look at these graphs and determine first thing, what type of graph is it? Is it a speed versus time or a distance versus time? Because both of them are going to give you different things. Next thing, if we have a horizontal line right here, horizontal line on each one. So the horizontal line on the left tells you
constant speed.
Constant speed. It's still moving,
But it's constant.
but it's constant speed. Now, if I had a horizontal line right here on the bottom, that would be when it's stopped or not moving. But where it's shown is the line at the top, that is constant speed, no acceleration. What about on the right side, on the distance time graph? What? A flat line, just like that, means you stopped. Okay? So the distance is constant, which means you stopped. Now right here, we're coming at a negative angle, so a negative slope. And that told us that we were slowing down. Well, what about the distance time graph? What if I had a negative slope right there? Does that tell you you're slowing down on a distance time graph?
You're going backwards.
Not necessarily backwards, but maybe back to where you started. Does that make sense? If you thought about this, okay? So think about a track athlete. So here's our track. Not a perfect track, but pretty good. And you start right here, correct? And you're going to go all the way around, aren't you? So you're increasing your distance up until that point right there, aren't you?
Yeah.
After that, what do you start doing?
You're going back.
Okay. So if I have a distance versus time graph, and I'm talking about this track right here, and you're running, that distance is increasing all the way there, and then you're going to go back to the starting spot, aren't you? So that's what I'm talking about. You're still increasing the time, but you get back to exactly where you started. Any questions about how to look at these two different types of graphs? All right. Thank you very much, and yay notes.
Yay notes.